Hello, my name is Doug Montgomery. I'd like to welcome you back to our monthly Fireside Chat for our Design of Experiments MOOC. Um, for those of you that are new to this and to the whole Design of Experiments MOOC that we run on Coursera, I host this monthly Fireside Chat with a guest speaker to talk about specific topics and applications of experimental design methods and concepts. We always leave some time at the end for Q&A. This is a great time for you to ask questions, and they could either be about the Coursera course or some specific situation or a problem that you're working on, or something that relates to the topic that our guest is going to talk about. Um, for those of you that are on Coursera, we post these fireside chat recordings to the courses. They can be found in the resources tab of your course. And we have a lot of them. We have, I think, something like 42 or 43 fireside chats. So there's a lot of really interesting things out there that you could get involved with if you would like to do that. Quick reminder, uh, please keep your mics muted and your cameras off during the session. We don't want to have too many disturbances. Barking dogs and crying babies are always kind of fun, but not not this morning. Okay. If you want to submit a question to either me or our guest speaker, uh, do this using the chat function on your Zoom menu bar. And you don't need to wait until the Q&A starts to put in your submission. You can start putting that in at any time during the session, and we'd kind of urge you to do that so that we can get those questions fired up during the Q&A program, part of the program. Uh, we try to answer all these questions during this time period. If we can't do that, we'll respond to it in Coursera for those of you that are actually enrolled in the Coursera course. Um, our speaker today is Dr. Caleb King from the JUMP Statistical Discovery Company. Uh, I'm really delighted to have Caleb back. He's been a guest speaker before. His PhD is in statistics at Virginia Tech. So he's like me, he's another proud Hokie. In honor of that, by the way, Caleb, I wore my Virginia Tech t-shirt today.
Very nice.
So, yeah, so I just thought I'd let you know that. His areas of interest include experimental design, reliability analysis, accelerated test planning, sample size calculation. He covers a lot of really interesting topics. Prior to joining JUMP, he worked for 3 years as a senior statistician at Sandia National Labs. Uh, Today, he's going to talk about covering arrays, which are something that are very widely used or should be widely used in software testing, and there are other applications. Um, this is, I think, a really important fireside chat for our course because we really don't talk about this anywhere in our Coursera course. And I don't really talk about it much at all in my graduate course on experimental design. And this is, in fact, it's not even talked about at all in my textbook on experimental design, which is crazy because this is such an important idea. And I really got introduced to this idea of covering arrays because for many years we had a faculty member here at ASU named Charlie Colburn. And Charlie was one of the real experts in this area of covering arrays. And I can remember a few years ago when I was on sabbatical and I was out at Jump visiting with one of our other colleagues there named Bradley Jones. And I was sitting in Brad's office and we were talking about something. And somebody knocks on the door and comes in, and it turns out it's another Jump statistician named Joseph Morgan. And he looks at me and he says, "You're Doug Montgomery." He said, "You're from ASU, right?" And I said, "Yes." He said, "You must know the great God Charlie." And then I realized that he is really quite a well recognized character in this world of covering arrays. And I did have the opportunity to work with Charlie a couple of times with his students, and brilliant guy. And anyway, I'm taking up too much of your time here, Caleb, but I just wanted to point out that I do have a more than just a passing interest in this topic, and I'm really pleased that you've agreed to give the talk.
Well, thank you for the invitation. And yeah, Joseph still every so often will drop Charles' name. We usually have regular weekly update meetings, so I think he's still doing some stuff with him. You might even see his name appear in this talk on some of the papers. But yeah, thanks for having me over.
Delighted.
So I'll go ahead and share my screen here. Okay, so you should be able to see my slides. Hide that. Okay. So you can see the title screen, covering arrays, secret to
I've got it.
successful
Yeah.
software training. Excellent. All right. So again, thanks, Doug, for the invitation and welcome everyone. I will start off with a bit of a disclosure. This is not necessarily my area of expertise. I actually didn't know about covering arrays until I came to Jump. Funny little story during the interview for this, Joseph Morgan was on the interview panel, and the question he asked me was about, do you know what covering arrays are? And I fumbled a bit because I knew what orthogonal arrays were. Covering arrays, this was new to me. And I remember coming away from the interview being like, oh, I probably didn't get it because I bombed that question. And well, I did get in. I got in as a tester. Um, and yes, so I learned so much about this topic. So a lot of the material I'm going to show you here is actually from some colleagues. So Joseph Morgan had a big hand in providing a lot of material. Bill Fisher is one of our newest developers. He's also been doing some research in this area, so he also sent me a lot of material. So there might be some points where I'll show you some articles. And again, if you're interested, I'd be happy to get you in touch with either of them or share some articles with you as well. So with that said, let's go ahead and get into it and start with a quick overview of what we'll discuss. There are kind of four things I mentioned in the abstract, if you read that. One of them I'm going to adjust a little bit because I don't think I'm going to take so much time on it. It might deviate a little bit. There's also a lot of information I'll make sure you're aware of, but that's on how they're constructed. I thought there'd be a little bit more, like with the orthogonal arrays and optimal designs, but not necessarily, or at least there is. I just don't have the time to go into it. So we will touch on that briefly, but mainly I'm going to introduce what is a covering array. Quick note on how they're constructed. I'd like to spend a good chunk talking about the different kinds of covering arrays that exist. There's actually quite a lot of variety. And then how to use covering arrays. I'll give you three examples of how we've used them here at Jump to kind of illustrate their use. So with that, let's start with what are covering arrays. We keep throwing this term around. What do we mean? Well, let's start with something that you probably are most familiar with, which is an orthogonal array. So for an array, you can think of a design. It's effectively number of rows, columns. So the columns are factors. So we have k factors. I'm going to assume for right now they all have the same settings. So they have v settings. If you want to keep things simple, let's assume v equals 2. So they all have two, each factor has two settings. And we're looking at two-way combinations. So again, keep things simple. You can think of t equals 2, all pairwise combinations. And one of the conditions is that if you pick any two of those factors, then every single possible combination of their settings together should occur exactly the same number of times, and that number is lambda. So we can write it simply using some notation here. N is the number of rows. So again, T, I believe that's the strength. I know for covering arrays, that's the strength. So the T, V to the K, that's just saying we have K factors each at V levels, and then lambda tells you exactly how many times those combinations should occur. So I've got a nice description. Some of you can probably get a good sense of it from there. I'm more of a visual guy. So let's look at an example. Here's an example of a simple orthogonal array. We have three factors, two levels each. So we can generate one in 4 runs. Lambda is 1, which means each combination appears exactly once. And to illustrate that, look at the first two columns. You'll see we have the combinations 1, 1, 1, 2, 2, 1, 2, 2. Each combination is present and present exactly once. If you look at the x1 and x3, you should see the same thing. There might be a different order, but they're all present. Same if you look at x2 and x3. Now, if you're really observant, you might notice that this is actually similar to a factorial design. If you replace the twos with negative ones, this is a factorial design in two factors, four runs, and an interaction term here at the end. Here we're using more of the notation that you use with arrays. So you've already probably been familiar with an orthogonal array. So now that we've got that under our belt, what is a covering array? You may notice I got some of the same terminology, but something has changed. Now, instead of things being exactly lambda times, it's at least lambda times. So now you're not specifying an equality constraint. Everything has to occur exactly this number of times. You're specifying a lower bound. And again, we can use similar notation. We're just changing one of the letters. And again, I can show you a quick example. In fact, I already have. The last one that you saw, that actually is a covering array as well. It's a covering array in three factors and four runs. And so that's nice, but it might be nice to actually see what is the difference between a covering array and an orthogonal array, because they're not always the same. So let's actually look at a different example. And to do that, I'm simply going to add in another factor to it. So let's look at four factors. Well, for four factors, I can create an orthogonal array in 8 runs. And in this case, now lambda equals 2. Now, I tried to find a case where I had four factors and lambda was 1, so each combination appears exactly once, and I couldn't. So I might claim that it doesn't exist. I might be careful with my claim, though, because it's just as far as I could find. But that does illustrate that when you're working with orthogonal arrays, there are restrictions. You are going to be limited in what you can do, and it's because of that constraint. So again, if you look at the first two columns, you'll notice that each combination appears exactly twice. And if you pick any two, that's what should happen. Again, you also might notice if you replace the twos with negative ones, this is actually a factorial design in three factors with one interaction term. I think it's the one between x1 and x3. But I won't go into too much detail on that. So we have an orthogonal array. What about a covering array? Now, again, the lambda is not an exact constraint, it's just a lower bound. Because of that, I can actually generate a covering array in four factors with 5 runs. So for example, if I look at the first two, notice that lambda is 1 here. And if I look at the first two, each combination does appear. It just so happens that the 2-2 combination appears twice. For a covering array, that's fine. It doesn't matter if it appears more than what I specified. Again, that's a lower bound. And so you already see the difference here. I don't have as many constraints, so I can get away with effectively fewer runs. And if you allow me to belabor that point a little bit more, I've got a little table for you. So let's look at several cases. I've got n as a run size and k as the number of factors. Now, these first two we've already seen. If you have 3 factors, you can get a covering array in 4 runs, same as an orthogonal array. And if you give me 4 factors, I can do it in 5 runs. But I want to expand this table out a little bit more just to show you how powerful a tool this is. So if you want to think of a comparison with orthogonal arrays, you could think of an orthogonal array as occurring in 2 to the k minus 1 runs. Now, if I have 10 factors, I can do that in 6 runs for a covering array. In fact, anywhere between 5 and 10, I can handle in 6. For 7, I can do it, for 15, I can do it in 7 runs. And as you keep going up and up and up, if you look at the very far right here, at the very far end of the table, I can generate a covering array in 14 runs that can handle over 1,700 factors with strength 2. I know it's insane how efficient these are. This is one of the reasons why they're becoming ubiquitous in software testing, or they should be more popular, I should say. They're just incredibly efficient. Simply relaxing that constraint and saying it just has to be present in this case, lambda equals 1, you have a lot of efficiency there. That trade-off is just crazy. Now, let's back up a little bit and maybe provide a bit more, we'll say, a fair assessment. Let's look at some of the pros and cons of covering arrays. So I've already illustrated some pros. One is that incredible efficiency. You can have a very, very large input space with the number of factors and get away with few runs. So really efficient. It also can be widely adapted. The same could be said of maybe orthogonal arrays or other types of designs. So there's a bunch of ways to adapt covering arrays to a variety of situations, and I'll be showing you that later. But there is one kind of drawback to covering arrays, and this kind of illustrates the difference between when you would want to use them. With orthogonal arrays, one of the reasons they're used is because you can distinguish factor effects. Because of that balanced structure that's present, and again, it's built into the name, that orthogonality, I can quickly identify which factors have a certain type of effect on the response. So it's really good for model fitting. And of course, that replication, again, helps if you have noisy processes. Covering arrays, though, the trade-off, you get much more efficiency than you would with an orthogonal array. The trade-off is that it's really going to be hard to do model fitting because things are kind of tied up with each other. So it's not really designed for the model fitting that you would do with an orthogonal array. It's designed for something else. So it's going to be difficult, not necessarily impossible, but difficult to tease out which factors are the primary drivers. Now I'll touch a little bit later on here in the chat about methodologies that we've recently been developing to address that issue. But that's just something to be aware of, is that kind of trade-off that you're making there. Okay. Now, I want to touch briefly on ways to assess covering arrays. So, with designs, especially with optimal designs, there's a lot of criteria that you can use. You can run through the alphabet. You have A criterion, B criterion, E criterion, E optimality, V optimality, C optimality, G optimality. There seems to be some sort of optimality criterion for any letter you want. So there's a lot of ways to assess, and there's things like aliasing, measuring the amount of aliasing with designs as well. So there's something like that for covering arrays as well. There are metrics that you can use to assess them. Here I'm going to touch on the most basic ones. There's effectively two that we can use. One is a pretty straightforward, obvious one. That's the T coverage. Again, the whole idea of covering arrays is we want covering efficient covering of the input space. T coverage then is effectively what percentage of two-way combinations are covered by the array. Now, if the T is the strength that you're using, so if I have a strength 2 covering array, then I should expect that the two-way coverage, or the 2 coverage, is 100%. That's by design. So where this really becomes helpful is if you look at 3-way coverage or 4-way coverage, because your array was not designed to cover all of those, but you might have two different covering arrays where one might have 3 coverage of, say, 80%, and the other might have 3 coverage of 60%. You might prefer the former because they both have the same strength too. They both perform that job equally well, but one actually has a bit more coverage of higher level interactions. So that's a way that you could use the T coverage, is how much does it do for higher levels of coverage? And of course, as you increase T, we expect the coverage to go down. But again, that's a way to assess it. Another one that's kind of a complement to it is T diversity. I've learned recently that this one isn't used as much, but there are ways to kind of use it. Effectively, what it's going to do is what percentage of those two-way combinations that are present, how many of them are unique? What percentage of them are unique? And I kind of view this as a way of saying, well, again, you're looking at coverage. So maybe for say you have strength 2 covering array, and you want to look at the 3-way combinations. So you can assess the coverage through the 3 coverage. The 3 diversity, maybe you have one where the 3 diversity is 100%. Every combination you see is unique. And one that might be 80%. I personally might prefer the former simply because if I'm interested in covering the space, well, I want to make sure that I'm doing that. I'm actually looking at different 3-way combinations versus another one where one of those might be repeated. Now, there might be a situation where you want that repetition, but if you don't really care too much about the replication, then that's where something like T diversity could help you. I want something that covers a bit more of that 3-way space and also make sure it's a little bit more unique. That makes sense. So as a quick example, if we take the covering array from earlier, that 5-row covering array, we have our coverage. So the 2 coverage, it should be 100%. That's the way it was designed. For 3 coverage, it looks like it covers just above 62% of the 3-way combinations. And for 4, 31%. For the diversity, you notice it's 80% for T equals 2. That means we do see some duplication. And that's fine. You should kind of expect that. For all of the others, it's 100%. So every combination we're seeing, whatever we've been able to grab from 3-way combinations, they're unique. There's no replication here. Okay. Now, as I promised, I'm going to have a quick blurb on how these are constructed. I did look into this a little bit, and in fact, the paper there that I've got on the screen, if you want to take a screenshot of that, that is a reference that does a really good job of surveying and summarizing a lot of the different methods used to create covering arrays. For the most of them, it's based on search algorithms. So I know in optimal design we have that, we have coordinate exchange, but there are some cases where you can directly construct them. For covering arrays, there are a few cases where you can directly construct, but for most of them, you are looking for doing some sort of search algorithm. And what are we searching for? Well, we're searching for what we call the optimal covering array. Basically, if I have two covering arrays that have the same strength, same factors and such, but one has a smaller run size, that's the optimal one. We want to minimize the run size for a given combination of factors. So again, do check out this paper. There are a lot of different algorithms that people use to try and find these covering arrays. I will say that we do offer it in Jump. Jump Pro has a platform that will allow you to generate covering arrays. And it will even generate an initial array, which you could try and then go on to optimize if it doesn't do it automatically. So that's my little jump plug for you today. So do check that out. But I want to spend a bit more time talking about all the different types of covering arrays that you might run into. So we've covered the most basic definition of a covering array. So what other variants are there? There's a lot of different situations that arise, especially in software testing. And so you can adapt the basic covering array idea to these different situations. The first one I'll talk about is a straightforward extension. It's a mixed level array. So you can imagine I have some graphic user interface, some GUI. Not every little knob and button on there is going to be able to be broken down into two levels. So I might have a drop-down menu that has 4 options to it. So I want to capture that. Maybe I've got something that has 3 radio buttons. I want to capture that. And I might have some check boxes, so that takes care of the 2-level factors. But I also might have some edit boxes, which means I get to pick however many levels I want. And so with the covering array, that can be easily handled. It just says, okay, well, I'll acknowledge that now some of the factors have different levels than others. But we can still maintain that property of, you just specify a lower bound of how many combinations need to exist, typically 1. So for example, here is a covering array with 9 runs. We have 2 factors with 2 levels, that's the first 2, and 2 factors with 3 levels, those are the last 2. And again, if you were to look at any pairwise combination, all the combinations of those levels should appear at least 1 time. So that's a straightforward extension of covering arrays, just allow different levels amongst the factors. The next one I find very interesting. These are called sequential arrays. These arise in a situation where what you're looking at doesn't really depend too much on what levels of the factor are present, but the order in which the factors are implemented. So you can imagine a certain process, a certain software where the order in which I press the buttons or the order in which I flow through it affects the response I get. Or the order might affect, if I do it one way, everything works fine. If I do it a different way, I get a bug. So in this case, the sequence is what matters. So then we can generate what's called a sequence covering array. In this case, instead of looking at all the two-way combinations of levels, we're looking at the two-way permutations of the orderings of the factors. And we have to say that those two-way permutations need to occur at least a certain number of times within n rows. So for example, here's a sequential covering array in 4 factors. Now here we don't have levels, we're just saying it's factor A, B, C, and D. And so here we're saying we're looking at the 3-way permutation of the factors. And again, they have to at least be present. So if you just say, pick 3 factors, A, B, C, we'll keep it simple, then you should be able to look through this and see that ABC occurs, ACB occurs, BAC occurs, BCA occurs. So all 3-way permutations should occur somewhere. They might not be right next to each other, but you should be able to pick them out anywhere in this array. That's what we mean by the sequence covering property. I initially was going to look at a 2-way one, but as it turns out, that's very simple. Just take a 2-way sequential covering array can be easily made by taking the ABCD, and then your next run is reverse everything. Now all 2-way combinations are present, so it's very efficient there. So I wanted something with a little bit more excitement to it, so I looked at a 3-way. Now the reason I find this one particularly interesting, some of you may be aware of this, but there's been a new field of research recently in the past 10 years or so called order of addition experiments. And it's the same idea where you have experiments where the order in which you put the factors matters. And that's interesting because that kind of came about independently of these sequential covering arrays. And I think the sequential covering arrays may have been around a little bit longer than order of addition experiments. So I've got another paper for you here. This one talks a little bit more about the sequential covering arrays. There's a couple also big names in the industry, in the area covering arrays here. So Dr. Richard Kuhn, Raghu Kakkar. I know Joseph Morgan, who you already heard of, name drops those people a lot. So those are other big names. But hey, if there's anybody out there who is familiar or doing research in order of addition experiments, you should be talking with the people doing sequential covering arrays. They should be talking to each other because you're talking about the same things with slightly different areas of expertise and areas of interest. So I really think that's a group that needs to be talking to each other. So hopefully maybe you can get in contact with some folks. The other type of array that I want to cover is a variable strength array. So imagine a case where maybe you've run a design and you want to augment it, or you're interested in more of a subset of the factors. So again, in the more traditional experimental context, you can do this through augmentation. Say, hey, I've identified some active factors. Let's look into that a bit more. Or you could try and generate the whole design to say, I want to focus on these a little bit more than maybe some of the others. That's the idea behind the variable strength array. In this case, I can maintain a nice global coverage. So let's say I want my strength to be 2. I'm looking at the two-way combinations. But for, say, 3 of those factors, I really care about those. And so for those 3, I'd actually like to make sure that their 3-way combinations are all present, maybe. So in that case, I have a variable strength covering array. Now, I don't have an example for you here. I did find one. It was 27 rows. That's still not big, but for PowerPoint, trying to show it there, that was going to be a little difficult. So I apologize. But basically, there are ways to construct them, maybe stacking some other covering arrays on top of each other. But effectively, you have a global coverage, and then for certain factors, you actually have better 3-way coverage than, say, other factors. So that allows you to kind of emphasize those a little bit more than others. So those are what's called variable strength arrays. And then finally, a quick run through of some other arrays. Some of these are being actively researched on, especially by members of our group here at JUMP. So there are constrained covering arrays. You could have constrained designs. Basically, what happens when some of those combinations aren't allowed. So if I have, again, the 2 ways and 2 levels, maybe I can look at the low-low combination, the low-high, the high-low. But if you tell me to do the high-high, I'm going to blow up the lab. So I can't do those. So basically, how do I maintain that coverage property when one of the combinations is not allowed? Or maybe I have 2 or more combinations that aren't allowed. So that's the idea behind the constrained covering arrays, making sure we maintain that while still allowing for some combinations to not be there. Then there's what I'm calling run constrained covering arrays. There's probably a better name. The best way to think about this is, well, what if I have a covering array and one of the factors is split plot factor or a whole plot factor, where I can't really make too many changes with that factor. It's really hard to do that. So I've got some constraints on the run ordering there. That's something that we're actively researching. I believe Bill Fisher, who I mentioned earlier, has a paper in the works on applying split plot methodology to covering arrays. So now you can have certain factors that are really hard to change. You can also apply things like blocks to covering arrays. That's another thing. A lot of the research in this area is effectively looking at what we have for sort of what I'm calling the traditional designs and saying, can we apply those to covering arrays? And how would that adaptation work? Because ultimately, at some point, that is going to happen. There's going to be something in the software where I can't really make this change very easily. So I could have a split plot type structure. And of course, as we encounter more and more unique test situations, different types of software being developed, there's going to be more and more variants of covering arrays. So this is still an open area for research. So there's always room for improvement in what we have. And so finally, now we've talked a little bit about the different types of covering arrays, a quick note on how they're constructed, what are they. Now let's talk about how they can be used in practice. So for that, I'm going to give you 3 examples from JUMP, because of course we work at JUMP. So that's where we've been trying to actively use covering arrays, especially in the testing of the software. But a quick kind of note on why is this very popular or should be more popular in software testing? Covering arrays, as far as I know, kind of originated in software testing. And there's two main reasons. One, we've already illustrated a lot of places of the efficiency in covering a large test space. You could have a very simple graphic user interface, but the number of inputs will grow quickly with that. And so we need something that can be very efficient. The other thing is typically in most software testing, when you run those combinations of factors, it's deterministic. If you run them again and again and again, you get the exact same output. Now, if there is a random component, obviously that's not going to happen. But for the majority of software, if I click the same buttons, follow the same process, it's deterministic, which is why we can get away with things like setting lambda equal to 1 and not worrying so much about the replication. It's because it's not necessary in this context. Now, if you start to apply it in other contexts, then we might need to think about that a little differently. But for the most part, we can get away with that because of that deterministic nature. So again, I'll cover 3 examples of how we're using covering arrays here at Jump or have used them. The first one concerns an add-in, or as we now call them, Jump extensions, to what's called XGBoost. XGBoost is a gradient boosting library. So there's a quick note here, and there's a reference there at the bottom if you're interested. We didn't develop here at Jump the XGBoost. I believe that was developed in Python or at least somewhere outside of Jump. What someone at Jump did do is create a graphic user interface to interface with the library. So for those who may be a little averse to coding, we're still learning it. There is an add-in available in Jump to kind of interface with that. And so here's a screenshot of what that interface looks like. It may not be the prettiest thing, but hey, it gets the job done. And as you can see, there are a lot of options there. There are a lot of edit boxes. There's a lot of drop-down menus. There is one checkbox, so there's one 2-level factor, but there's a lot of things where you could have different levels going on. And in fact, here's a table showing you all of those inputs and how many levels they've selected for that. So you can notice that most of them actually are set at 3 levels. There's the one or two that have 2 levels, actually more than that, sorry. There's one at 4 levels, and then there's one here that actually has 6 levels. So as you can imagine, the input space is very big. Actually, you don't have to imagine it because I've calculated for you what that input space is. This is how many total combinations there are if you wanted to test them all. So if you'd like to make a full factorial design, there's the run size you would need to achieve. I know it's bigger than a trillion. I believe it's 2,600 times bigger than a trillion. And I think we can all agree that no one in their right mind would ever have enough time or feasibility to explore all of these combinations. It's just not happening. The universe would end before you're done. So that's all the combination. That is our input space. I can create a covering array, and if I keep it at strength 2, I can do that in 25 runs. I can cover that input space in 25 runs, at least ensuring all the pairwise combinations are present. And not only that, with that particular covering array, I have 72% of the 3-way combinations covered and roughly 35% of the 4-way combinations covered. So that's not bad. Now, if I was interested in more interactions, so maybe a strength 3 covering array, okay, now I can do it in 150 runs. That is bigger, but I mean, if you compare it to the entire input space, it's nothing. So it does require a bit more runs, but it does have, hey, better coverage at 4-way. So again, you've got options here. But we ultimately have a lot of efficiency in testing this very complex interface. So that's the main takeaway with this example. This next one is a little bit interesting. It concerns one of the key flagship features of Jump, and that is our profiler. If you've ever used Jump, you're familiar with this. If not, it's a sequence of graphs. Each graph has an input, so you have some function that takes multiple inputs and can have one or more outputs. And these graphs are interactive. You can have a little handle. You can either edit and put in a number, or you can drag it around. And what makes it interesting is that as you drag it around, yes, the response changes, but if there are any interactions present, as you drag it around, the other graphs will change their shape accordingly. So it really allows you to explore this multidimensional function very easily. Another reason why people like it is there's the option to optimize settings. So I've run an experiment, I've identified the key factors, and now I've got this profiler showing me here's how all those relate. there's something called optimized desirability. I set a desirability function. It can be increasing, meaning I want to maximize. It can be decreasing, I want to minimize, or it peaks at a value, meaning I want to match a target. And once I specify that, I can tell Jump optimize that. And what it's going to do is it's going to do a search and then return to you the settings that optimize that. So I can return the settings that give you the maximum response if you're interested. Now, early on, one of the things that was kind of troublesome with it is that if you did run an experiment where you had the disallowed combination, I can't put out these two settings or I blow up the lab. Well, what could happen is the profiler is not aware of that initially. So if you tell it to optimize, it can return, hey, here's the settings that will blow up the lab. Well, I'm sorry, Mr. Profiler, I can't do that. Well, to the profiler's credit, again, it wasn't aware that that was a thing. So recently we incorporated that. So now the profiler is aware that it will look in the table and say, hey, if there's any disallowed combinations, I will respect that. I will make sure that the optimal settings I give you don't include those combinations. So that's very nice. But of course, we need to test that and make sure that that's accurately being done. This is what makes this interesting. Here's the factor levels. Now, most of these factors have nothing to do with the profiler. That's the last three factors. The first few factors generate tables. So think of if I create a covering array from this, each row of that covering array creates a design. So I have a design that creates designs is effectively what I have here. And so again, each of those is specifying what types of factors, what type of models, what type of simulation am I doing? Am I augmenting this design or not? What constraints are present? So those are the factors. That's just what made this quite interesting. And this was something we published a paper on in a special issue a while back. And again, just to emphasize, if you wanted to cover the entire input space, there's over 1 million possible combinations, so much less than the previous one, but still a lot. And we can construct a strength 2 covering array with just 13 runs, which is helpful because we have a nightly run here at Jump where we do nightly testing. It'd be nice to keep it very small because we have a lot of things we have to test. Nobody wants to have to run 1,000 tests for one thing overnight. So that's another example of where we've used it and we're actively using it still. One last example, and trying to make it good on time here. So another platform that we introduced, I believe it was introduced in Jump 16, I could be wrong, but we have the custom design platform, custom DOE platform in Jump. Very powerful tool, very flexible in helping you create almost any design you would want. But it could be a little intimidating for someone who's new to design of experiments. So we created Easy DOE. It's a platform that walks you through how do you pick your factors, what model you're kind of working under, that helps inform the design. Okay, we make you the design. Here's a table, fill it out. You get to see how the responses are acting as you fill it out. Then we walk you through the analysis. And finally, we help generate a report saying, here's everything you did. So it walks you through the process very easily. There's also a more flexible version for advanced users who just like the ability to document their flow. But it was created for beginners in mind. Now, again, we'd like to test this. So here at Jump, we like our covering arrays. So we are going to generate a covering array. Here's the factors. We got a couple things at 4 levels, one at 5, one at 2. Now, in this case, I'm not going to necessarily emphasize all the possible combinations and the efficiency of the covering array. I think I've hammered that point a lot. Here, I want to focus on something else. So there's our test suite. There's our covering array, 29 runs. And you'll notice one of them is highlighted. We found a fault. That's nice software speak for saying a bug. Something broke. Something did not match right. We found an issue. Now, I'd like you to see if you can determine, based on that one fault, what was the factors that caused it. Good luck. So that is an issue of what we call fault localization. How do we identify what caused the fault? How do we localize the factors causing it? And again, recall that I said one of the difficulties with covering arrays, we overemphasize the coverage part, that we kind of miss out on that being able to distinguish. Now, if I had a couple more faults, I might be able to distinguish that a little bit better. In this case, I only had one. So that's going to be incredibly difficult. Well, as it turns out, back in 2023, Irene G., she was an intern at the time. Now she works as a full-time developer for us. And her advisor, Simon Mack from Duke University, developed a Bayesian approach to help with this fault localization issue. And they, of course, called it Bayesian fault localization. That's the official name. What I think is the better term that they use is Bayes flow. Bayes fault localization, Bayes flow. And what I want to do is kind of walk you through how that works, because now we have a tool that actually helps us with the fault localization. So that starts, as most Bayesian methods do, with assigning the priors. And there's a lot of info here. A lot of it's just breaking out notation. But the main thing you just need to know is for each level, you're going to assign some prior probability of that being a root cause. What is the probability that A1 is the root cause of a fault, or C2, or E2? So everybody gets a prior. Here's an example of how that could work. So I've got some inputs where I'm like, those aren't really going to cause much of an issue. So I'm going to assign them a very small prior to begin with. And I've got some, those might be problematic, but not too problematic. So I'll bump up the prior a little bit for that one. And this guy, I'm eyeing this guy. He's a little suspicious. I've had bad experiences with this guy. So I'm going to bump him up to be the highest, not too high, but he's trouble, I think. So we've got our priors. Okay, we've set those up, and it's fairly straightforward to do. Um, and then, well, what about combinations of those levels? That's what we care about. And again, that's pretty straightforward. So, for example, what's the probability that A1 and B1 together cause a root cause a fault? Just multiply their priors together. That's sort of their marginal prior probability. And so that's how we can compute the probability that if something's involved, if one factor is involved in certain combination, k-way combinations, well, it's just the product of all their priors together. And of course, then we need to compute a posterior. I'll refer you to the paper. You can look up Bayes flow in their paper because most of it is dealing with, well, how do I compute this PE guy? Because there's a bunch of combinations I need to work through. And they come up with a really good way of efficiently doing that. I will admit most of the slides I'm using here, I kind of copied over from Irene's presentation on this. So I apologize if I'm not going into too much detail. But the main takeaway is that at the end, you get a table that looks like this. So based on those priors you specify, and then our one fault that we found, we can identify that, hey, this combination here has the highest posterior probability of being a fault. That means that the tester can run their test suite of tests. They'll get their faults. If they get any, ideally not. That would make the developers very happy. But if they do, then instead of having to pass it and say, hey, there was this bug, and then it's up to the developer to kind of figure out what's going on, they can give the developer a head start by saying, based on this, the faults that we're seeing and the priors that we've specified, this combination seems like it might be causing. And so that way the developer can get a head start and maybe look at that and say, yeah, I know exactly what's going on here, and they can go fix it. So that's very beneficial to us developers. And I'll also mention that as of Jump 19, Jump Pro has Bayes flow installed as well as a feature. So let's wrap things up here. Covering arrays, they should be much more popular in software testing, maybe in other areas as well. And the reason they are is they are an incredibly efficient tool for software testing, especially. They've already been adapted for a variety of testing situations, kind of like what's been done with design of experiments. And we're also adapting stuff from design of experiments, traditional design, over into covering arrays, as I've already mentioned. And this development of Bayes flow is a key step in addressing that fault localization sort of weakness of covering arrays. This is still an active research area on ways to improve this Bayes flow technique. There may be other techniques out that come out because of that. So ultimately, there's still a lot of room for R&D in this area. There's still a lot of room for research. And maybe, hey, maybe I've inspired you to take a look into it. Maybe you'll have the next great idea for covering arrays. And with that, I will end there. Thank you for your time.
Caleb, thank you. This was extremely interesting.
Mhm.
And as I said, this is a topic that we really don't talk about anywhere in either the MOOC or in my graduate course or in my textbook. And so I hope that this is going to be very informative for people that are interested in applying experimental design methods to things like software testing.
Mhm.
And I'm sure there are lots of other applications. I can see applications involving the assembly of systems,
Mhm.
where the number of components that are used at each stage
Right.
have an effect on either the reliability or the performance of the final product. So there
Mhm.
should be some applications there, I think.
Yeah,
Yeah.
that'd be interesting to look at.
Yeah, and I don't think we have any audience questions, which is too bad because they're missing an opportunity to talk to the real expert. One of the things that I wanted to ask you about,
Okay.
uh, and I know that covering arrays don't really provide useful information for model fitting,
Hmm.
but I know I used to talk with Charlie Coburn about this
Hmm.
a lot. And we always thought that there was probably some worthwhile project involving how do you take a covering array and then augment it somehow with runs
Right.
that would enable you to support at least some sort of primitive model, like a
Right.
main effects model in certain
Hmm.
factors. Maybe if you've had test combinations of your covering array that showed failure. Uh,
Hmm.
you take the factors that are involved in that, and then try to figure out how do you augment your covering array with more runs in those factors, so
Right.
that you could maybe fit some sort of simple model.
Hmm.
Is there any work going on in that particular domain that you're aware of, or is that something that really should be an interesting research project in your view?
I definitely agree it should be a research project. I definitely see it as another example of adapting stuff that we have in, again, I keep calling it the traditional design space over to covering arrays because I think there still needs to be a lot more of that. Um, I personally don't know of any research. I could reach out to some of my coworkers to see.
Yeah.
It wouldn't surprise me if there was, and I just hadn't heard about it. But no, I definitely agree that that's definitely something to consider. Is how to augment a covering array.
Yeah, Charlie and I thought about that. We just never really got around to doing much with
Yeah.
it. But it would seem to me that something really simple like a de-optimal uh,
Hmm.
augmentation for being able to fit, say, a first order model in
Right.
in those factors might be useful, and it might not require that many runs. Uh,
Yeah.
because at that point you've probably reduced the size of the
Mhm.
of what I'll call the factor space
Right.
down from a whole lot
Mhm. Right.
down to a very few.
Exactly.
Yeah, yeah. Uh, the other place that I wonder whether these designs have some application is in an area that I've been doing a lot of work in the last few years, which has been funded by the Defense Department, and it's been in finding ways to efficiently do operational testing.
Mm.
Um,
Yep.
the uh, Back in the 1960s, Congress passed a law that said that the Defense Department can't field a new system until they take the sort of the end stage prototypes out into the field and do full scale operational testing. That is, you turn them over to users. You investigate how they work under different kinds of test conditions. It could be anything from environmental to actually operational, and you have to demonstrate that the system actually works as intended.
Right.
And these turn out to be fairly large experiments, and complex experiments, because you typically need a test range of some kind,
Hmm.
and you need proper instrumentation and operational people, and you often end up looking at lots of factors.
Right.
It's not unusual to have these experiments involve, 8, 10, 12 factors,
Right.
a lot. And
Hmm.
so what we were looking at was the idea of using uh, small non-regular fractional factorials to
Okay.
be able to do this, and we've had a fair amount of success with that. And
Right.
but on the other hand, I keep thinking that really what you're interested in is the coverage. You
Hmm.
know, it. When you're at this altitude, okay, if it's an air to ground weapon system, if you're at this altitude and the target is this far away, okay, and the angle of attack is this,
Hmm.
what you're really interested in is the probability of hitting the target.
Right.
And so you're not so much interested in modeling, but it's the same sort of outcome.
Hmm.
Does it work at that set of conditions?
Right. Right.
And I always kind of thought that maybe we were sort of missing the boat with the traditional 16 run fraction. We tended to concentrate a lot on 16 and 20 run designs
Right.
because that's about the feasible limit of what you can afford to do when you get out to the test range. If you come in with a 40 run experiment, the people that run the test range just laugh at you because and the other thing is sequential experimentation is not really very possible.
Hmm.
So you run an experiment and you say, well, gee, it could either be this effect or that effect, and I need to do additional runs to separate the aliasing. And you say, well, I need to do 8 more runs. And the people that run the test range look at you and say, well, yeah, you can have 8 more runs June of next year.
Yeah.
That's when we have time. But
Right.
it would seem to me that covering arrays might be a way to absolve yourself of having to make some of these kinds of decisions. And I just never really had a chance to get into that. Um,
Hmm.
and now our project is sort of in limbo.
Okay. Yeah.
Yeah, well, the thing is, it got renewed in 2024 for 3 more years.
Uh,
And then we got the funding for 2025, but no funding for 2026 has come through.
okay.
The the office that manages this project has gone radio silent, and so and which is too bad because there's still a lot of really interesting questions that we'd like to get answered, and this is one that I always wanted to sort of get into.
Hmm.
And never really had any uh, in any resources to do that.
Yeah.
But anyway, I just curious as to whether you think that would might be those kind of problems might be a viable area for covering arrays.
It might be because what you described is very similar in some ways to what you see in software testing, where again, we're trying to identify the faults. In this case, for the operation, you can have a certain definition of what you'd say a fault is for that one, and in that case, they're going to be very similar. I think the differences would be that in the operational testing, you'd expect more of a noisy process,
Yeah,
so that if I repeat things, maybe you could overcome that by that lambda value. Instead of it being one, it's two now or something. So
right.
you enforce some replication in there.
And
And
you're
if
right.
you
There is going to be noise in the system
right, yeah,
because the second time you fly that sortie, you might get a different outcome.
yeah. So you could try something like a covering array with the lambda equals two, and there may be an application of sort of this base flow methodology, especially if you're not going to be able to necessarily augment. You kind of now have to work off of, well, this is the array I've got,
Right.
and so I need to be able to inform, uh, again, what's the likelihood of that certain things are causing issues. So I think there might be potential there. I think that would actually be something interesting to pursue is how something like a covering array, when you increase that lambda, compares to the designs you've been using,
Yeah, and if
and
we
what you
can
can
do
get
it
from
in
that.
fewer runs, that would, of course,
Yeah.
be
Oh yes.
absolutely incredible because
Hmm.
each run is very expensive because
Right.
of all of the resources that you have to bring into play to actually
Hmm.
do the test. You've got to have the hardware, you've got to have operating personnel, You got to have all of the ground facilities, all the monitoring. I mean, it's just hideously expensive, to do this.
Yes. Yes.
And you can't avoid it because you're required by law, you know.
Right.
But on the other hand, it is important to do it because um, the example that I use that illustrates the importance of this is our new fighter aircraft, the F-35. Uh,
Hmm.
the F-35 is the only aircraft that we have ever had since since the F-4 Phantom Vietnam War era that's
Wow.
flown by all three services.
Mm.
Yep. The Air Force, the Navy, and the Marines all fly this thing. And of course the F-4 Phantom was wildly successful. I mean, it was just a fabulous airplane. Just you can't say enough good things about the Phantom.
Right.
And of course, the hope is that the F-35, which is stealthily, it's got all sorts of wonderful technological advantages. This is the next wave of this kind of aircraft. Well, it turns out that when the early prototypes went to operational testing, the first thing they discovered is that the Navy and Marine Corps versions would not land on the aircraft carrier. The tail hook's in the wrong place.
Uh-oh.
They're too far forward.
Yeah.
And now it's a good thing they discovered this before they built 500 of them,
Yeah.
right?
Right.
And fixing this was actually not terribly easy because the exhaust nozzles move around. They're directionally adjustable, which improves the maneuverability of the airplane.
Right.
So figuring out how to do this, how to fix this was non-trivial. And you wonder, is this the sort of thing that they should have discovered in computer modeling, but they
Hmm.
didn't.
Right.
And so this is why you have to do this operational testing. But it would be nice if we could figure out, instead of having to do 16 runs, or 20 runs, could we do this in 8 or 12?
Right.
Well, it's a huge savings in time and money.
Hmm.
So I'm very hopeful that
Yeah.
maybe we get to spend some more time thinking about these kind of problems. And I may be coming back to you and asking you and
All
some of your
right.
jump cohorts to
Yeah.
to get involved with us
Okay.
because I think it's an area that has a lot of potential.
Hmm. Yeah, absolutely. Sounds like it.
Well, I certainly appreciate your spending time with us today.
Yes,
I
I
really do.
appreciate the invite.
And I'm so happy that you were um, able to take time out and do this, and give my regards to Joseph Morgan too.
Will
I
do.
haven't seen him in a long time, but
Yep.
but I've always greatly respected his work, and I'm as I have yours,
Yeah.
and
Thank
and
you.
I really appreciate your spending the time. And don't be surprised if I come back and ask you to be a guest again.
I'd be surprised if you didn't. So
Well, hopefully we'll find a topic that'll be of interest. Thank you so much.
yeah, certainly. Thank you.
Okay, bye bye.